I am Vishak, and I am a PhD student at IIT Kharagpur. So this work is a collaboration between IIT Kharagpur and IBM Research. In fact, my co-author Ramakrishna was supposed to be present in the conference in person and to present the paper, but unfortunately, due to certain health issues, he was unable to attend. So I am presenting this paper, which is on finding common certifiers in a privacy-preserving way. So often in enterprise scenarios, there are situations where two companies can make use of some offerings from the other company. And on the basis of that, they might be willing to strike a deal. So a company on the left-hand side, S1, needs X, and the company on the right-hand side, S2, has that. Similarly, S2 on the right-hand side needs Y, and the other company can supply that. So this could be a basis for a business relationship. But there are usually questions involved, such as can the other company be really trusted? And what if they defraud us? So an indication of such trustworthiness can be obtained if somebody who is associated with one company is also associated with the other one. So on the basis of the presence or absence of such a common association, there can be a deal or no deal. Now, while determining these common trusted associations, it is fine if only the common ones are revealed. So we call these trusted associations as certifiers. So for example, here, a government agency B or a scientific organization N are common certifiers. But there can be other organizations also, such as the political organization M is not a common certifier. And interestingly, often these associations can be sensitive, such that this company on the left-hand side might not want to reveal it to the right unless it was something that was in common with two. Or it might also happen that one party might gain some business leverage by getting to know some of the certifiers of the other party. So overall, it is very important to preserve privacy while determining such common certifiers. So in the context of Web 3.0, there have been ongoing efforts to standardize decentralized identity and decentralized credentials. So decentralized identifiers, or DIDs, are a W3C recommendation that lets users create, own, and control their digital identifiers. And these DIDs are typically stored in decentralized registries, which are often implemented using blockchains, however not necessarily. In conjunction with DIDs, more importantly, verifiable credentials or VCs, which are also a W3C recommendation, allow credential issuers to attest claims about DID holders. Then the DID holders can present and prove these claims to verifiers through verifiable presentations. Overall, DIDs together with VCs solve a real problem of establishing trust in a decentralized setting. However, we can observe that during the presentation of a verifiable credential, the party which is carrying out the verifiable presentation process inherently also exposes the issuer and the presentation certificate to the other party. So this leads to potential loss of privacy for the party who is presenting first, while the other party has actually nothing to lose. The problem is with the infringing asymmetry in this procedure of verifiable presentations and verifiable credentials, requiring one party to expose its certifiers and which are issuers, as well as the certificates to the other party first. Therefore, the goal of this work is to find a solution for privacy-preserving symmetric exposure of certifiers as well as certificates. So, the key question that we try to answer through this work is, can parties owning certificates efficiently identify a common set of certifiers without leaking anything else? And we call this problem as Private Certifier Intersection. So the problem is to allow two or more parties having a set of certifiers and a set of certificates which are issued by those certifiers to compute the intersection of the certifiers while also validating the certificate. And it has to do all these things without revealing anything which is not in the intersection, that is, without revealing the certificates or the certifiers which are not there in the intersection. We consider that the participants can be malicious, they can lie about their certifiers, but they cannot forge the certifiers' signatures on certificates. In addition, any solution protocol that we come up with must be efficient enough to be used in practice and preferably on commodity hardware. So private set intersection or PSI protocols have been studied extensively in the literature, and PSI protocols allow two parties to compute the intersection of input sets while revealing only information about the elements which are there in the intersection and no information about the elements which are not there in the intersection. So PSI sounds very similar to PCI, right? So the question is, can PCI use PSI as a building block? The answer would be yes, but only assuming semi-honest adversaries. So if we assume semi-honest adversaries, then each participant maps its certificate set to the certifier set, and then the participants run PSI on their certifier sets. But our threat model is more stringent. For the threat model with malicious adversary, the certificates need to be validated. Otherwise, one party can simply input all well-known certifiers, which is essentially the universal set, resulting in knowing the entire input set of the other party. Therefore, PSI cannot be simply used as a black box for building PCI protocols. So we introduce and define three variants of PCI. The first one is PCI-Any, which finds the intersection of certifiers who have attested some claims, that is at least one claim about the holder. The claims might be different for different parties as well. However, the claims are not revealed in the process. The another variant of PCI is PCI-Any disclosed claims, or PCI-Any DC, which is essentially same as PCI-Any, but here the claims are revealed during the process. And the PCI-All variant finds common certifiers who have attested all the claims about the parties. Here also the claims are disclosed. So if you think about it, in the limiting case, if there is only one kind of claim that this certifier attests to in a certificate, all these protocols are identical and simply output the common certifiers, which is the general notion of PCI, Private Certifier Intersection. So our key contributions in this work include a formal definition of PCI in the Simplified Universal Composability Framework, ECDSA framework, which actually enables using PCI as a building block for other larger applications in a composable manner. So we develop a practically efficient PCI for certificates using ECDSA and BLS signature schemes. Both ECDSA and BLS are very popular and are used in many existing applications, which also includes applications on blockchains. So we designed PCI-Any, PCI-Any DC, as well as PCI-All protocols for both ECDSA and BLS signature schemes. And the BLS PCI-All protocol is particularly efficient because of the signature aggregation property. And we propose the protocols for two parties, and we also provide extensions to the multi-party variants. Please have a look at the paper for more details. So the core building block of our PCI protocols is MPC for elliptic curve pairings. So we introduced efficient secret-sharing-based MPC over elliptic curve pairings, and this works for malicious security and dishonest majority setting. We developed new theoretical constructs and extensions to the native MP-SPDZ library to support elliptic curve pairing operations. And apart from these, there are many other optimizations, such as optimizations in the implementations allowing concurrency, etc. And more details are there in the paper. So we implemented and open sourced two PCI protocols for ECDSA-based certificates and two-party protocols for ECDSA-based certificates and two-party protocols for BLS-based certificates. So in the paper, we also propose extending these two-party protocols to multi-party PCI. And these protocols are secured against malicious productions of dishonest majority. So if we take a look at a simplified overview of PCI-All, we can observe that a key optimization here is validating aggregated signatures within the MPC framework. So I will be going through all the details. I will be already presenting a simplified overview here, and the detailed protocols are there in the paper. The two parties have their sets of certifiers and certificates, and they first aggregate the signatures coming from the same certifier over different claims. Now, these aggregated signatures, along with the public keys of the certifiers, become the private input to the MPC. As the claims become the public inputs to the MPC. So after validating the claims and matching the certifiers, PCI-All outputs the intersection. And neither the certificates nor the public key of the certifiers, which are not in the output intersection set, is revealed. In order to implement the PCI protocols, we extended the MP-SPDZ framework for elliptic curve pairings. So we have open source implementation, and the code can be found at this link. So for evaluating the performance of PCI in realistic settings, we deployed the parties in AWS instances having 8 core CPU and 8 GB memory, and these specifications are close to commodity hardwares. So we deployed the parties in 3 data centers spread across 2 continents, one in US West Coast, one in US East Coast, and the third one in India. Now let us go through some of the performance results of PCI. So these 3 plots show the end-to-end latency for PCI-All with fixed input size of 100 certifiers per party. And this is done for LAN, WAN, and intercontinental WAN setups with latency varying from 1 millisecond to 62 milliseconds to 186 milliseconds, which are the round trip times. So the key observation here is that with the increase in the number of claims, the end-to-end latency of PCI-All for ECDSA signatures increases. However, the same for the BLS signature schemes stay unchanged. This is because ECDSA has to validate each claim certificate from a certifier individually. But with BLS, PCI-All is able to validate the single aggregated signature per certifier. And this validation of aggregated signature, which is key optimization, is only possible because of our extension of the speed MPC framework for elliptic curve pairings. So next, we can also have a look at the overheads in terms of data volume communicated for PCI-All and the memory overheads. So here we see the same trend that with the increasing number of claims, the memory consumption and the data volume communicated overhead increases for ECDSA variant. But for the BLS implementation, these overheads stay more or less unchanged. But in general, if you observe that for low number of claims, BLS implementation actually consumes more memory. So taking a step back, we arrived at this problem of private certifier intersection on the way of solving the problem of DLT interoperability. So in this problem, there are 2 separate blockchain networks which need to swap and transfer assets or share ledger data with authenticity proofs. And this data sharing or transfer of assets relies on the ability to prove or verify claims about the counterparty ledger states. So to enable such claim verification, syncing of identity information is necessary across the blockchain network. So such syncing of identity information is possible with the help of verifiable credentials, which are supported by the decentralized identifiers and the DID registries. So the problem of DLT interoperability can be thought of in 2 separate planes. The data plane, which is concerned about the swap and transfer of assets or sharing of ledger data, and in the identity plane, the identity informations are being exchanged. So the PCI protocols actually contribute to the identity plane, where it allows the 2 blockchain networks to find out the common certifiers in a privacy preserving way. There are several exciting future directions from this work, such as implementing and benchmarking multi-party PCI, then supporting different types of credentials beyond the regular ones, such as BBS plus certificates, and then support for advanced functionality such as private claims and prioritized output of the certifiers. So IBM Research is contributing towards the Viva DLT interoperability project, which is soon going to be combined with the Hyperledger Cactus project, which will be called Hyperledger Cacti then. the PCI protocols are actually a building block towards the identity plane in that project. So thank you, and I'm looking forward to your questions.